Perfect. Hi everybody, my name is Nabeel Sarwar. I'm a machine learning engineer at Comcast NBC Universal. Today I'll be discussing how to deploy Spark along with other technologies in order to create a metadata-driven, reproducible, consistent, decoupled, and multi-phased feature creation pipeline and model execution pipeline. You can consider this an extension of my previous Spark Summit talk where I talk about the more abstract level of feature engineering, and here I'll be talking about how you actually operationalize it. Let's get started. So I'm part of the customer experience team, so all of my use cases revolve around customer experience. In terms of customers, Comcast is a lot. I'm sure you guys have heard of it. We have about 27 million customers, give or take, a few million, that all employ various different amounts of our services. We ingest a bunch of data all the time, a large amount of machine-generated but also customer-generated events. Thus, we needed a data science pipeline to be able to operate at this scale for all the different use cases and to basically make it reproducible and shareable and democratic. We started this effort about a year and a half ago, and we grew very quickly, and I think this approach that we did not only let us scale from a technology side, but also from a people side as our organization grew. So within the Comcast Applied AI division, we work on various different use cases, anywhere from video to customer service, home security, and we employ all this different data in terms of improving our video analytics, abstract data science, NLP, and content discovery and recommendation use cases. So to give a side of the business problem, you need to improve customer experience. You need to solve all these issues proactively and quickly and efficiently. Like I said, we have a bunch of different services, so there's a bunch of different domains, lots of different subject matter experts spread across the organization that don't know what each other's doing sometimes. And secondarily, in addition of improving customer experience, we also want to reduce the cost of the business by being super efficient, possibly by reducing technician visits to the home, or just by automating things that are being done already. So to give an ideal use case of what AI would look like, it needs to be interactive for us, predictive, and proactive. So the main portal for customers to interact with the data science pipeline that my team created is by the virtual assistant. So if you go to the App Store, actually, there's a My Account app, and if you use the virtual assistant, you can actually ask it questions. And these questions will then lead on to calling our NLP model, and then predictions being delivered to the customer or to our systems to improve customer experience. So how would the virtual assistant work? So you would have yourself typing in or chatting into the virtual assistant section. The NLP leads to our domain models. The mapping to the domain models happens, and my stuff gets called. So my team is in this device data ingest to predictive AI ML pipeline. Once we deploy the prediction, this goes back to a decision engine, which I won't talk about, and that leads to actually improving customer experience. So you guys know the business problem. So what actually is the technical problem I'm trying to solve? We have multiple programming and data science environments that all need to be coalesced, all using different sorts of tools. We have white and discordant data sources throughout the company that all need to be regularized and put in the right temporal, right partition structure. We have data that's coming both at rest, in batch and in stream, coming from rest and data in motion. This needs to be consistent. Whatever is done during training needs to be exactly what's done during prediction. I'm sure you guys have all heard about the data science problem of data drift and model drift. And lastly, everything needs to be versioned because I need to be audible to my stakeholders, transparent towards everybody, and document for myself. So to give you guys a use case to have in the back of your head the entire time, we'll start with a very simple Comcast typical internet use case. So let's say you had poor internet and you were wondering what's going on. You would go to the Xfinity speed test portal, launch a speed test. This would automatically trigger a prediction flow, which would launch our feature creation pipeline, which then leads to execution of an ML model, predicting whatever it is, and giving such a response back to the customer. All right. In addition to the actual data science problem, there's also a sort of business problem where we don't want to make things worse. So for example, let's say we were scheduling a truck roll to go to a customer to fix some issue outside the home, right? And let's say that you had 3 neighbors that all suffer from the same issue from the same outside cable, right? We don't want to send 3 different truck rolls to 3 different customers to fix the same issue when we can just correlate up and bubble up that prediction toward a higher level. So the technical problem then becomes 2 main challenges. Feature assembly, actually doing feature creation and feature engineering responsibly and democratically and reproducibly. And in addition, not making things worse. Notice that I don't mention model building. Model building is surprisingly the easiest part, as you guys have probably seen from other talks. So for the first problem, we need to standardize features, action, and rewards, and also create a feature store for access to historical and online data, so the data scientists can train on the historical, and so that I can look at the online data when we actually need a prediction for a customer. So to give one quick run through what this would look like on the business side before I go to the technical side, you have your business owner, your stakeholder, whatever, the guy with the money. He defines a use case. He goes to the data scientists start doing exploratory analysis. They go to somebody like me to start creating more production-ready features so they can start looking at actual production-ready features. We iterate to create models. Let's say that all goes well, we don't need to iterate. We go check it into the business user. The business user looks at all the different models the data scientist creates, sees the different trade-offs the data scientist made in certain situations, actually selects one. Then my team would create the actual production-ready pipelines in our sort of stage prod environment, along with all the different nice things you want in production, like scalable assembly, pipelines to do post-prediction metrics, and also model deployment and monitoring to detect model drift and data drift. Lastly, we go into pre-prod, where we evaluate performance in a sort of dark environment to make sure that what we deploy is actually useful. This is sort of like your dark A/B testing. Lastly, we go live once the guy with the money says, yes, this is good. Oh, wait, pictures. So all of this was done to solve 4 different problems. We wanted our platform to be self-service. We wanted data scientists to not have to talk to me at all. We wanted to treat models as code so we can use our standard tooling like GitHub and all the standard linting tools. We also wanted to make sure that data scientists and business owners were aligned with production. And lastly, we needed to make things actually work fast in a scalable manner, which is probably what you guys are interested in. So I keep saying the words metadata-driven. So why did we choose a metadata-driven approach? So this approach was inspired by a technology called ground context that came out of Berkeley's RISE lab. And basically, what it's looking at is at 3 different layers for each app. It's looking at the application context. In machine learning, this would be all the statistical parameters, callbacks, the media data you think of machine learning, like the features, where they're coming from, how they're transformed. You also have the behavior context. This tells you what data you used, what code you used to transform it. In addition, in the behavior context, you also have metadata that tells you which upstream sources are giving you the data and how they affect you. And we don't do it right now, but we should also be detailing how our downstream sources use our predictions. Lastly, the 3rd layer of this context layer is the change context, where you version pretty much everything. We version every transformation, for example, if a raw data source changed the version, we would keep track of that. We keep track of every single version in our POMs, whatever, requirements.txt. Everything's versioned. Anything that touches the pipeline has to be versioned. And we do this because we want the metadata to drive what and how the code is ran without us having to interact with it in order to truly deliver a self-service platform. This is a Spark conference. I need to tell you guys how we're using Spark. So on the left side, we have our training pipeline. So imagine you have your raw data coming in. It goes into our metadata. It gets versioned. And you push it to a historical raw data store in Alluxio or S3 or whatever. Then the data scientist creates a feature creation module, which then leads data to be in disk or memory, do some more analyzation, and create a model. Then, once we have our feature creation pipeline and model checked in, we can actually do this such thing in production. So each arrow in this sort of diagram is a place where Spark could go. So here you have Spark Structured Streaming, Spark Batch, and Spark Model Deployment. And I'll go into more detail into each of these different blocks later on. One thing which we definitely needed was a feature store to do this at scale. And by feature, here I'm talking about a machine learning ready feature, something you can put in an actual prediction function. So we have two kinds of feature stores. We have an online feature store, where you can get the current value for each entity, whether that be a customer, device, or node. We also have a historical feature store, which is pretty much append. This is where the data scientists would look at to start building models and to improve already running models. In addition, this is where data scientists would look at work done by other data scientists to reproduce or extend their work, or just reuse it in a different use case. So the online feature store is used, like I said, at prediction phase. It needs to be fast ingest and fast query. And our historical feature store can just be anything we dump into, so Alluxia or S3. And we also maintain our raw data separately. So our online feature store always overwrites data, so we always have the current value. And our historical feature store, we add everything to it. It's always appending. Pictures, okay. So how do we actually use the online feature store? So going back to the VA example, the virtual assistant example, the virtual assistant, somebody calls in like, hey, my internet's really bad, what's going on? The decision engine, the NLP model will tell us what model and what account number we need to use it for. The model metadata will tell us exactly what features are needed and how they're needed, and I'll go into this in detail. And this then goes into a feature assembly step where we pull in all the features from the online feature store and transform them as needed, if needed here. Like I said, everything's decoupled. And then we pass everything for model that's assembled for model execution and prediction. You can think of each arrow as a different Spark process so that we can do transformations and feature engineering and model execution at any step with our metadata driving exactly what's being executed. But before we can actually execute anything, we need to have features. So to have features in our online feature store and our historical feature store, we've separated our features into two kinds of features. We have continuous features, which are always on, always aggregated, always transformed. And we have our on-demand features. And these two features would all be handled by the same streaming framework, which would be Spark Structured Streaming. Currently in our production, we run different frameworks because Spark wasn't ready, but with Spark 2.30, we're pretty much going to replace everything. So looking at the aggregated and continuous features, these would be things that are like the number of times people have called over the last days, Fourier transforms of the device signal over the last 24 hours, things like that. And they would go into your structured, into your streaming platform and then go into your feature writer. In addition, we also have on-demand features. Not everything can be collected all at once. Some things are really expensive to collect. Like, for example, if a customer is having issues or not having issues, I don't want to constantly spam their set-top box or cable modem for really specific device data that might impact their customer experience. And for these things, we need to specify a time to live. That's what TTL stands for. And we collect these things using Apache NiFi, Apache Flink, and Apache Structured Streaming. So what does the feature metadata actually look like to enable this process in an automatic fashion? You need to have your basics. You need to know what the feature, how it's even identified. So you have a namespace name and version. You also have your JSON path evaluations and your script references. These would all be the feature engineering or parsing or whatever that you would do at any step at feature ingest, or sorry, raw data ingest, pre-model transformation, model-specific executions and stuff like that. We also need to denote how we're going to partition and store this data. So we have feature metadata in terms of how we're going to salt the data once we put it on S3, or how we're going to extract it in, for data scientists. In addition, we depend heavily on temporal features because everything customer experience is time-based. So for each event we ingest, we tabulate how we're going to specify its event, ingestion, and processing time, in addition to other relevant timestamps. No pictures, perfect. So to give an example of how a feature would be ingested, you have a raw feature which would have its header, which say like the internal customer identifier, like the account number, the address, whatever. you have your timestamp, and you have the actual meat, the JSON payload, which would be like, the actual raw data we transform. So these would be, in our context, the speed test results. This would go into the feature ingestion pipeline, which then, using the metadata, transforms it in exactly how we need it as a data scientist denote it to then push to whatever store we need. In addition to the feature metadata, we also have model metadata. So the model metadata is very similar. It has identifying information. Excuse me. It also has environment parameters, such as how we're executing it, whether it's a SageMaker endpoint, some Lambda function, whatever. It also defines any additional feature engineering that needs to be done, such as maybe you want to do, at this level, model-specific dimension reduction or model-specific encoding. And here we also define the time to live for each feature, because different models might have different times to live for the same feature. And lastly, we also specify how the model is going to be deployed, things like the auto-scaling options, when to shut it down if it's going too badly, basically our safeguards and our business as usual. One thing that's really important for consistent and reproducible data science is that you need to have consistent data and know exactly where it's coming from. So we set up a culture to place everything in S3. We did experiments with Alluxio, but we found it was easier to do political flexing to move people to S3. We also need to define the metadata storage parameters, which I said before. All of our streaming operators within our streaming framework are metadata driven, which will specify how exactly to transform it, where to load scripts from, and where to save data to, or to what stream to push to. We also have a historical store, which, like I said, stores our raw data and our engineered features. Lastly, everything needs to be versioned, and the metadata also denotes how things are stored in order for us to know which version of which data is where. In addition to just having consistent data, you need to have consistent feature engineering. So we need to have the same feature engineering at training versus prediction phase. The data distribution must be exactly the same, otherwise nothing will work. We use the scripts that the data scientists check in during the feature metadata checking in process. This is where they would define the features, how they transform it into TTL. And we also define exactly how to transform it from raw features to actually do it in production. One thing that we really love Spark for is the consistent feature engineering. We've been using a few different frameworks, like I said, Apache Flink and Apache NiFi to deploy a lot of our feature engineering. And we found that it was really difficult to make data scientists be unified. So one thing we really love Spark is the Spark SQL. With it, we can replace as many operations that data scientists use for their feature engineering with their SQL equivalent for when they check in. This way, if they check in some code, we don't have to translate that code into a different streaming framework or a different deployment framework. We can just deploy their code as it is, as long as they follow our standards. And there's no need for them to learn a DSL. We tried some experiments with data scientists using our DSL to call our feature engineering functions. They didn't really like that. An additional thing was that Spark is an excellent unifying language for deeper feature engineering. So as long as our data scientists are all using Spark and not doing feature engineering across different frameworks, we can deploy their code as it is in a self-service manner. In addition, we reduce a framework jungle. And by using this consistent feature engineering, we can do feature engineering at every step. This way, we can truly have a decoupled and multi-phased pipeline. We can transform data at post-ingest, in flight, or at rest when it's ready for prediction, before it even goes into a model. And these standards will fit to both streaming and batch once we use Spark as a unifying language between Spark structured streaming and the Databricks notebooks environments that our data scientists would use. So I've talked a lot about metadata and features, so let's actually talk about what things usually think of machine learning, the actual models. So when it comes to models, we support various different paradigms. We support H2O AI POJOs. There was an excellent H2O AI talk before. I really recommend it. We support deploying Spark ML models. We also support deploying simple Python scripts via REST endpoints or specialized TensorFlow models, for example. We support various different deployment environments. For example, we support deploying in Docker containers behind REST endpoints so that the feature assembly is easy, it's containerized, and anybody can call it without having to use our feature creation pipeline if they so needed. We also deploy as map operators within our streaming framework. Like I said, this is Apache Flink, but we're doing experiments with Spark Structured Streaming. We're very happy. We can deploy it as Lambda or SageMaker Spark functions on AWS. I know this is not, and this wouldn't be AWS agnostic. We also support them as Spark launchers, and the benefit here is that we can also do additional feature engineering. And the Spark launcher would be launched from some sort of Java web framework like Spring Boot or something. And we are also doing experiments and have tested out doing our retraining phases when we detect data drift or model drift by using the Databricks jobs API, and then having that sync in with our CI/CD pipeline. All right, so with all that context, what does it actually look like in production? So let's go into the VA says, hey, I have a bad internet issue. Somebody tells me a message in Kafka to know what exactly to execute. My feature assembly step would then read, are all the features in this streaming framework current? Let's do the easy case where some features aren't current. Like let's say this model uses both on-demand and continuously aggregated features. Some of the on-demand features might not be there, right? So then the feature creation pipeline will, in an independent manner, go and get each independent feature in an async manner and push that to whatever it needs to go. Some of the features will be current. Like I said, we push continuously aggregated features all the time, so they're always current. So then, after the feature assembly is done, we do the actual execution of the model, where our streaming framework will do an async call or an inline call to the model execution. That's leading to a prediction going to our prediction store and our customer context. So features of the ML pipeline, like I said, we try to make everything metadata driven, and through this approach, everything's traceable, repeatable, and auditable, fully transparent. Our metadata-driven approach lets us just do easy CI/CD with deployment, because the data scientists themselves determine how to deploy the model through the self-service manner. And we're mostly AWS agnostic, except for a few endpoints. So we can mostly switch everything over without any hassle. And lastly, for the next steps in future work, we want to do additional work with model and metadata management in a UI portal. Right now, people have to look at our database. We also want to do more containerization for additional model execution environments. We want to integrate better with Databricks notebooks to enable workbench for the data scientists within the actual deployment environment, and also add more for continuous model monitoring. One thing which I mentioned before was we want to be completely democratic. So we want data scientists to look at work done by other data scientists and be able to leverage it. So this UI portal would enable data scientists to search for features done by different namespaces and use cases, and search for them by importance or whatever. And we also want to do more work at determining first-class tools. Right now, we're pretty much letting the data scientists determine what is needed, but I'm going to start doing more things pushing back on them. In addition, we're doing stuff to do automation of the retraining process. So in summary, I'm not going to say it again. You guys have heard the words metadata-driven way too much. Everything's automated. Everything is iterative through our self-service consistent manner. We enable rapid onboarding because we use the same tools that the data scientists use. Everything's consistent because the data scientists don't have access to any other data besides the ones we produce. And we're adding monitoring and metrics. This is more of a half block. And with that, that's it.
Can you please come to the mics for any questions?
Hey mate, thanks for the talk. I had a question around speed. So when the feature ingestion pipeline, when it goes through everything, say it has to compute stuff, like how long does that whole process take?
Well, it's really, really fast. So as long as you use something like Apache Flink or Spark Structured Streaming, as of version 2.30, we have a latency of about 2 seconds from coming in to get an actual prediction. And an additional second for it to get to the actual iPhone app.
Hi. Your metadata store, what are you using?
We're using Postgres to store all of our metadata.
Okay, and how do you get data there? Do you get it from different teams?
We've enabled an API that data scientists can call, so they can define their use case, the model metadata, and within the model metadata, they would define the features. So you would first check in your features, then you would say this model is using these features through the API, the REST API, and then you would define the use case, and then that's all you need. After that, it's pretty much scalable. We require data scientists to have a few fields selected, like for example, the location of their scripts on GitHub, so we can load them in CI/CD manner, and also the location of their versioned data sets, which is why we're building a UI portal, because we don't want the data scientists to use an API to just check in their models.
And what is your data store, like data set, where are you storing your data
Oh,
sets?
we're using, for querying data, the online feature store. So for the historical feature store, we're using S3. We were using a little bit of Alluxio. We were exploring with it, but we politically flexed to use an S3. And for the online feature store, we're using a combination of RDS and queryable state within Apache Flink.
Hi, Naveen. Thanks for the presentation. So my question is on how do you enforce your data scientists to use a CI/CD pipeline, and like say, what is the format in which they have to specify their models? Because I can write a model in R, I can write it in Python, or even I can use C++.
Yeah. So right now we make the data scientists use only Python and Scala Spark, and basically as long as they check in their UDFs and their window aggregations, they won't need to do anything else. They just need to do those two things. As long as they check in the UDFs, we can load in the UDFs and run it in our, in our map operations.
So do they need to define all the input-output for the UDFs?
Yes, they do, yeah. The data scientists have to define the schemas
In the
and
custom
everything.
format?
Excuse me?
Is it in the custom format, or do you use any kind of PMML format to define certain things?
No, we're using mostly class definitions, no PMML, and data frame schemas, and some Mavro.
Okay, thank you.
Did you mention that you use Spark inject to Postgres directly when you inject the features?
Yeah, so basically what would happen is the feature assembly would do an async call to the database to assemble all the different things, if they're there, or otherwise execute the model. And then after that, we send the assembled features on a Kafka or Kinesis stream that the model would then execute. In addition, we also support, once you have the features, calling in REST endpoint, then we then send the features as a post response, and then from there we do a Spark launcher to actually execute, convert the JSON to a data frame and then actually execute the prediction. So we support both deploying to a Kinesis stream or via a REST endpoint.
So I assume when you do feature engineering, you're using Spark and then write directly into the Postgres
Yeah,
database.
exactly.
And Postgres handles well?
We had some issues with the more scalable models, so we moved things a little bit to Apache Flink queryable state, where we can just query things really fast.
Thank you.
Hi, could you please elaborate on model versioning?
Oh yeah, sure. So the model version might include, we would increase the version number if the features changed, if the pipeline changed, if any of the transformation changed, or if the endpoint changed. So right now we're just increasing the last number by 1, and then just one. For example, if model was 1.0.0, we just make it 1.0.1 at any small change. But yeah, that's any small change to the model execution layer, or any small change to anything will increase the version of the entire pipeline.
Is that a metadata storage or?
Yeah, that would go in the metadata.
Okay, thank you.
All right, thank you.